Good afternoon, everyone. Welcome to the Commodore Theater. My name is Jeannie Larkham. I'm currently the president of the Portsmouth Friends of the Library, and we are sponsoring today's speaker. And if you're interested, we do have membership cards on the table over there where Todd Elliott, our library director, is standing. We also have free bookmarks. Membership for individuals is just $10 a piece. So if you're so inclined, we'd love to have you as new members. We also want to recognize our group of homeschoolers that's come to join us today. We're so glad to have some young people with us. It's wonderful. I'm also told by Todd that today is Stephen Hawkins' birthday. So it's quite an auspicious beginning to our series. And again, the Friends of the Library has been sponsoring the January Forum for some time, and we're delighted to be able to do it. We do have a monthly book sale in the basement of the main library for any of you who are interested. We sell books by the inch. It's $1.25 an inch for hardback and 75 cents an inch for paperback. So on that note, I welcome you all again. It's a new beginning to another year. They go by so fast anymore. Anyway, Mary?
Good afternoon. Thank you all for coming. My name is Mary Hodges. I am co-chair of the Second Tuesday Forum along with Sue Burton. And I also work here at the Portsmouth Public Library, and I'm so glad you all could join us. And now I would like to introduce our speaker, Michelle Shin. She is the Chief Optical Scientist of the Free-electron Laser Division, and she has been at Jefferson Lab since 1995. Jefferson Lab's free-electron laser, often referred to by its acronym FEL, is created using an underground particle accelerator, and the laser is directed to laboratory rooms above ground. The FEL is the world's highest power tunable laser. As Chief Optical Scientist, Dr. Shin sets the specifications and analyzes the performance of the FEL's complex optics systems. In addition, she has led design, procurement, and installation activities for upgrades to the free electron laser. She also collaborates with other scientists who use the FEL, and in particular pursues her own research on laser applications, as well as on the laser-induced damage of optical components. Before coming to Jefferson Lab, she was a physicist in the laser division at Lawrence Livermore National Lab from 1984 to 1990, and associate professor of physics at Bryn Mawr College from 1990 to 1995. Recently, Dr. Shin was named a Fellow of the American Physical Society in recognition of her contributions to the application of lasers in society. In her free time, she enjoys time spent outdoors as an amateur astronomer, bird watcher, and beekeeper. Please, everyone, help me welcome Dr. Michelle Shin.
So, I guess I need this thing turned on. Can you hear me? I don't hear it.
That doesn't go to the house, just to me.
Oh, it does?
Oh, so the house microphone is on the phone.
Oh, I didn't know that. Well, can everyone hear me? Actually, if I stand away, can everyone hear me still? Yes. Awesome. Well, I used to lecture, as Mary was saying, I used to lecture to classes all the time. So we don't have microphones. So therefore, we just have to make do. And my voice tends to carry, so that tends to work out.
But you can take the mic off the stand if you want to.
And I may do a little of that, but it kind of constrains me. So anyway, I would thank you all for coming out, and I'd like to thank Mary and Todd and Sue for inviting my... I beg your pardon? Oh, thank you. I'm not used to these. I wanted to thank Sue and Mary and Todd for having me come out and speak to you all. So the title is Exploring the Structure of Matter. And I think exploring is a great verb, because when we explore, we think of folks like Lewis and Clark, right? Or Daniel Boone. Whereas if we said researching the structure of matter, you'd think of people like folks on Big Bang Theory or maybe the professor from Back to the Future. That doesn't sound too exciting. But actually, I have a very, very exciting career. we have a very exciting program at the FEL and at Jefferson Lab, and so that's what I want to talk to you all about. So in part, what I'd like to do is acknowledge who funds the lab. In actuality, you fund the lab through your tax dollars. But that is funneled not from you personally, obviously, but it's funneled through the Department of Energy, through our contract, through the Commonwealth. The Commonwealth gives the laboratory and the free-electron laser money so that Commonwealth scientists can come out and work with us. The United States Air Force and the United States Navy have all funded us. And then we have a group of the forces, Navy, Marines, Army, et cetera, called the Joint Technology Office, and they also give us money. Next, please. So what I'd like to do is walk you really quickly through the outline of my talk. So I'd like to give you an introduction to Jefferson Lab. So the full name is the Thomas Jefferson National Accelerator Facility, which sounds really big and fancy. It takes too long to say. So we say Jefferson Lab, and actually what we normally say is just JLab. So I'm going to talk to you about JLab, give you some history, what's our purpose, demographics, some funding, a few things that are important to do. But then really, what are we doing here? What we do is I'm going to give you a very brief introduction with no equations, just pictures, to nuclear physics, so you can all say that I know what a quark is. Well, actually, we don't completely know what quarks are, but you certainly will know what a nucleon is. And the way we do it is we have some very, very unique accelerators. The accelerators that work at Jefferson Lab are the first of their kind in that they use superfluid helium working at 2 degrees above absolute zero. And we have something on the order of 19,000 gallons of that stuff flowing through our pipes. And all of the new accelerators like the LHC are built on the technology that was developed and pioneered at Jefferson Lab, which is essentially in your own backyard. So what are the advantages? And so I'm going to introduce you to superconducting radio frequency acceleration. We just say SRF. And then I'm going to tell you a little bit about free electron lasers, because that's what I do. And it's a lot easier to talk about what happens when I melt fat than it is to explain to you about gluon interactions. Yes, ma'am? Speak into the mic like that? Sure. Thank you. All right. Why are the free electron lasers special? And then I'm going to talk to you about the experiments we do. And so there's going to be materials research that we do, and then I'm going to talk to you a little bit about dark matter, because that's sort of a mystery, dark matter. And then my conclusions. Next, please. So we are one of 17 national laboratories and facilities around the country, and as you can see, I've got a nice picture that was a graphic provided. What is special about the Department of Energy? The Department of Energy is the largest supporter of physical sciences in the United States. The DOE directly funds 40%, and then everyone else, it's parts from the NIH, the National Institutes of Health, parts from the National Science Foundation, parts from the Office of Naval Research, and so on. But the DOE is the largest. So you can see all these labs, some of them are very famous, and I think actually that where we are at Thomas Jefferson, Jefferson Lab, we're pretty famous too. And that's where we are relative to everybody else. Next. So at a glance, what I want to do is we have this pie chart, and most of what we do is contained in here. It's nuclear physics. If you're from my part of the world, we go nuclear, but I'll try to say nuclear. I've been trained. It takes a little training though, because believe me, 27 years in Oklahoma. And what we run in that blue section is CEBAF. So anybody who's been in Tidewater for a while knows that we weren't Jefferson Lab forever. We were the Continuous Electron Beam Accelerator Facility. And CEBAF is what we call the big machine, the big accelerator. And CEBAF is interesting because I'd have to sit there and I'd be talking to some vendor and they'd say, so where do I send this packet to, ma'am? And they would go, I'd say, well, it's C like in continuous, and E is an electron, try to spell it all out. And then I'd get something addressed to CBAS. Go figure. But we got called CBAS a lot, and I think that just got easier to put JLab. Like all of the national labs, We are not directly run by the Department of Energy in the sense that we are not government employees. We are contractors through the Jefferson Science Associates. And the important thing are our capital, our people. So there's 800 full-time equivalents. Those are folks that work there all the time, permanent employees. And what you see down here is that we have a number of students, a number of faculty. That was one of the most important things in the creation of Jefferson Lab, is that we would have faculty, we would be training students, we'd be training the next generation of scientists. Now, they don't all go, when they're all done, they may finish up with nuclear physics, but then they may go on and do some other type of physics. So this is very important training ground on how to do science. And our K through 12 science education model is one of the best in the nation. For you folks, because a lot of you, I understand, are from the homeschool program, have you been to our website? Any of you?
Middle schoolers, that's what they studied.
Great, so I just heard the middle schoolers, that's what they study. We have a really nice portal to the education, and it's got all sorts of stuff that will allow students to study for their SOLs and things like that. Next, please. So economic impact. Beyond those 800 people, we have about 1,300 scientists that come from all over the world to use our machine. They bring in special equipment that costs sometimes tens of millions of dollars, run their experiment for a year or so, and then pack it up and leave. To build our machine, to run these experiments, all these people that come in and spend money in the Hampton Roads area leaves a nice impact. And what you can see is just year to year, on order, we do $200 million per year to the nation, and that's our economic impact. We've grown a lot because we're building a lot. We are increasing, we're doubling the energy of the machine. There are all sorts of buildings that are going up to run these experiments, to store the hardware, et cetera. So there's quite a big impact to the nation, and more importantly, to Hampton Roads. Next, please. So I'm going to walk you through what's called the Accelerator complex. This is the part that you'll get to see once every 2 years. We have open house. And Michelle Leckman, my friend and colleague, wave your hand, Michelle. So she's one of the organizers of this amazing setup where we invite you all to come in for about 6 hours and get to walk through the tunnels and kick the tires, so to speak. Have you been?
I haven't. When's the next time it's open? Every 2 years.
So it'll be about a year from this coming April. We just had one.
All right.
So Michelle, what I'm going to start with, so this is some of the new building that's going on right here, and we have a new building here. And what this dotted red line does is it's going to walk you through, I'm going to walk you through the accelerator really fast. So the electrons start here, and they go through a linear accelerator, which I'm going to talk about, and they gain energy, and then they coast in a big arc, and then they accelerate again, coast, accelerate, coast, accelerate. We do that up to 5 times. But we don't have to. We can just do one time, and we can separate the beam and say, send it into Hall A. Simultaneously, just a few nanoseconds, a few billionths of a second apart, comes another stream of electrons that can go into Hall B. And then nanoseconds, we can send another beam into Hall C. So we can run 3 beams all at once into 3 different halls. And now we're adding a capability to go to yet another hall, the brand new one over there called Hall D. And we're going to now walk you through some of the parts. So Michelle, if you'll hit the button for me. So the first thing is what lies underground, some 35 feet underground, anchored to a bunch of shells that are called the Yorktown Foundation, are these devices called cryomodules. And I'm going to talk to you about what's inside the cryomodule. In fact, you'll see that on the next slide, which are the superconducting radio frequency, or SRF cavities. So note those, note that shape, because you're going to see that shape a few times. And they're all nice and shiny because they're polished niobium. Inside the halls in Hall B, actually this class, this large circle of detectors has just come out, and it's getting replaced with a brand new one, a better one. Next. This is where I work, where I spend most of my time. It's in the Free-electron laser facility, and there's our cryomodules sitting down there. And I think there's one more, Michelle. Yes, and then Hall D, which is I show as being constructed. We actually have now taken beneficial occupancy and we're shoving stuff in. So we're getting ready to do experiments in a couple of years. So what do we do with the nuclear physics? What does this accelerator do? Well, the accelerator you can think of as like a microscope. So if anybody thinks about it, what limits how small, how tiny can you see with a microscope? Has anybody ever thought about that? Well, if you think about it, you think, oh, well, I can get a lens. It's the size of my lens, right? But it's more than that. It's actually the wavelength of the light. How short? What's that shortest wavelength? Because you can't go shorter. You can't actually image. You can't see something that's smaller than the wavelengths of the light you're looking at, or the energy, so to speak, of the light. What we've done is we use electrons, which are the smallest objects in nature. We actually don't know the size of an electron. We argue that an electron is actually basically a perfect mathematical point. But if you could put a period and then put 18 zeros behind it, and then a 1 and a meter, that's how small, it has to be smaller than that. So how do you study that? Well, you need to study that with a very powerful microscope or with a lot of energy. So what we do is, as we all remember from our science classes, the atom consists of a nucleus with electrons around it. Now, we represent these electrons going in these orbits. It's actually more complicated than that, but this is a good representation. If we take that nucleus in the middle and we look at it, what we know is that from our experiments that were done in the 1900s, that the nucleus is composed of protons and neutrons, right? But if you go deeper, we know that if we slam protons, for example, into this, we see, or electrons, we see all sorts of other particles come out. So what's going on? And what we've decided is that within each nucleon, a nucleon is a proton or a neutron, there's actually these things called quarks. And so what happens in a nucleon, or we call them actually baryons, a baryon, like a proton or a neutron, has 3 quarks in it. I'm sorry, the fermions do. And so the question is, why don't we ever see a quark alone? We know that structure. We know there's 3 of them in there. And we know that because of how we balance charge. Neutrons are neutral, protons are positive. So we know that there's something in there, and why can't we ever pull them apart? Because if we try to pull them apart by putting more and more energy into it, just like setting off dynamite, right? You're gonna punch hard, and what happens is when you start to pull them apart, the energy that you're using to pull them apart actually creates a whole new pair out of nothing. That energy converts to mass. Remember, E equals mc squared? So all of a sudden, a quark and an anti-quark appear, and that's a meson, and bingo, hey, I've got 2 more quarks bound together. You never find that isolated quark. Why? That's what we're trying to study. Next, please. So I'm going to give you a quick little primer. I already showed you a graphic, and my little primer is that what happens is the primary family. So what I was going to say is that if I hit a neutron or a proton hard enough with an electron, I scramble the quarks. So the quarks get all mixed up, and what pops out is one of several different families. And the families can be this, the baryons. Baryons are us. You're made up of baryons. You can tell your mom and dad, hey, I'm made up of baryons. Baryons mean heavy in Greek. And so they're made up of 3 quarks, whereas mesons, which are considered, these were all just soup to us. We called it the zoo back in the 70s. Those are actually what are called bosons. They have no net charge. And they're made up of a quark and its anti-quark. So that's like the sister, so that there's no net charge. If you do then say, well, okay, leptons are then what's left. So I've got protons, I've got neutrons, but then what are electrons? Well, electrons are called, those are the leptons. And then finally, I can pair these up and say that if I have bosons and I have fermions, those are called hadrons. So keep that in mind, because what have we all heard about? The Large Hadron Collider, right, over in Europe? So now you know what a hadron is. So now you can say, I know what the LHC means. The LHC means that I'm studying with this big accelerator, I'm studying hadrons, and hadrons are made of bosons and fermions, and you know what both of those are now. They either have 2 quarks or 3. Next, please. You can actually go to the website, and I'll give it to anybody, particularly the students, and there is a free download of this beautiful chart that you can print out, or you can buy for cheap, but for teachers and educators, and that means everybody in homeschool can download for free a version of this. So I'm just pointing it out. I'm not going to go through it because we don't have the time, but I do just want you to see that. Okay, next. Okay, so how do we accelerate our electrons? So remember I told you a minute ago that we have these pretty niobium cavities. And so what we do is we inject into those cavities microwaves. And these microwaves, kind of like the microwave in your oven, we put it into a cavity, and what you see is that the cavity has these, I show these arrows, and you see the arrows are flicking back and forth. What happens is the waves bounce back and forth in the cavity, and sometimes they collide in such a way that you have a net push along the direction of the electrons, which are those little flowing bunches of dots, or sometimes they go against it. So what we do is we time the electrons so that every time they enter the middle of a cavity, it's pushing you forwards. What we like to say is that we surf, our electrons surf on an accelerating gradient or on an accelerating voltage. And what you see is that when there's this brief period, you notice when all the arrows disappear, that's when the electrons drift through. So they're always timed to make an accelerator. Next, please. So we were the first. So the deal is, great, there's lots of accelerators around the world. And they mostly use copper. Copper's cheap. But the problem with copper is that it resists electricity. So when I shove in that power, that electric power, that RF power as we call it, when I shove that in, what happens? They get hot. And when they get hot, what does hot stuff do? What does hot stuff do? You remember what happens when you get something hot? Does it expand? Does it get bigger? It gets bigger, it expands. So when it expands, we say it goes out of tune. Does anybody remember when you take your radio and you're all tuned into a station, right? And then you're driving down the road on the older tuners, and as the car got hot, what happened? You had to reach over and retune the radio. Everybody remember that? We had to retune our radio when it got warmed up? Well, that's what happens to a copper accelerator. So what you can't do is you can't just run it all the time. You've got to shut it off. So you run it for a few thousandths of a second, then you wait, and then you turn it back on again and run it a few thousandths of a second, and then you shut it off. So imagine what would happen if you could run it all the time. And the way we do that is we make our systems superconducting. And when they're superconducting, they have no resistance. So to do that, we have to cool these down to liquid helium temperatures, which is, as I said earlier, was 2.1 degrees above absolute. So we can't just leave these cavities and this helium flowing around on the floor. It would vanish right away. So we have to put it into these big vessels, and these big vessels we call a cryomodule. And these accelerator units, these cryomodules, are then strung together. You can see this one, and then up over here is yet another one, and then there's another one over here, and we call that a linear accelerator. Next. So what happens is we form a linear accelerator, or we call that the LINAC. And in the original CEBAF, we had 20 cryomodules in each LINAC. Remember, I showed that long straight section? There were 20 cryomodules on each side. But now, in our upgrade, we're going to 25. So now there'll be 25 in each LINAC. And then the free-electron laser LINAC has 3 cryomodules. And again, we were the first to do this, right here in Newport News. And so the CEBAF is used for nuclear physics, and the free-electron laser is used for basic and applied photon science. We do a number of things. I would say photon physics, but it's more than just physics. And so I'm going to walk you through some of those. Thanks, Michelle. Next. So lasers, we talked about that. Ability to use an accelerator to study matter. Well, you can use lasers to study, particularly pulse lasers, to study matter too. And to sort of reveal that, I'm going to do a little demo, which I probably should have had out. How many people have a camera? Either in your smartphone or you have a camera like this. So just imagine, it's really, really dark. So what do? If it's really dark, you turn your flash on. And so what does the flash do? The flash takes something which is previously invisible because it's dark, and it makes it visible. So by using a flash laser, a pulse laser, whereas the microscope, the accelerator was like a microscope, the laser is like a camera flash. And so I can stop the motion of something. Now you might say, well, how fast is that motion? Well, in matter, solid matter like this chair, or more importantly, stuff like crystals like in my ring, matter travels, those processes occur in trillionths of a second, or even less than a trillionth, 1,000 trillionths. So we need really short pulse lasers. And different laser types can be used to answer different questions. Well, it turns out that we can use our accelerator to make a very special laser. Michelle, next. But before I get into that, I want to talk to you about lasers. Because everyone thinks, well, I know something about lasers, I use lasers. But what's the deal? What's different about a laser than, say, this flashlight? Okay? So the big difference is one of the things is called coherence. Now, if I take my flashlight and shine it, that's a regular source of light. So what happens is these light-emitting diodes that are in this flashlight, every part of that diode is emitting, and an electron over here that's emitting a photon doesn't care about what's happening to the electron somewhere nearby. So that's just like, if I try to add up all the different waves, I end up getting some little wave. The other thing about these lights is that they don't stay sharply focused. So this is nice and bright, sharply focused on my hand, kind of weak by the time it gets there. On the other hand, lasers, nice and bright on my hand, nice and bright on the screen. And you see it doesn't get very big. So what's happening is the sources in this laser all act like one point. Even though they're radiating from different points, they all work together, kind of like a marching band. And it's like I've given in my example in my slide, think about the ocean waves. Ocean waves are more or less coherent. So think about, have you ever been knocked down at the beach by a wave? Anybody remember that? That's coherence for you. Okay, Michelle, thanks. Okay, the other thing is that light from a laser is monochromatic. It's one color. And to prove that, I'm going to do another demo. I'm going to take, this is my grating. This is called a disperser of light. And we all have these at home, right? And you can see, as I flash it, you can see all these different colors, right? Now watch what happens when I use the flashlight versus the laser. Can we make it any dimmer? Can we make it dimmer in here? Oh, I thought it was going to get dimmer. Oh, it would? Oh. All right, well, I'll shout again. So I'm going to take this CD and I'm going to shine this light on it. And what I want you to do is watch what happens. So here we have this. And now I'm going to take the CD and I have to look for it. The problem is that in the dark room, it's very easy to see this in a darker room. Michelle, can we turn off this turns right off, right? Do I hit this button? Oh, darn. Well, the problem is, thank you, somebody. There, look near the curtain, near the left curtain. Do you see that band of green and blue and red? So there's red. Here, let me get back to. There they are. Now, what happens? So, white light is dispersed into colors. But what happens when I take the laser light? The laser light will become a stripe. Let me get that. There we go. There's the stripes. There. But you see, it's only one color. It's always green. There it is. See that green stripe? So with the light, with that flashlight, I had three colors. The primary colors from the diodes. But with a laser, it's just green. That's one of the big differences. That's coherence for you. Okay, so now we're back on. And would you go ahead and would you advance?
That's going to take a minute for this.
True. So while we're waiting for this to warm up, are there any questions partway through?
Maybe you could re-explain what you just said about the light in the microphone.
Oh, okay. So for those that didn't hear me shouting, so what we saw with the flashlight is we dispersed with the CD, we broke the light. I'm not going to say dispersed. We broke up the light into its colors. Did you see the green, blue, red? That makes white. With the laser, we could not break up the color because it's only one color. So that's a big difference. Lasers are coherent, and lasers also have this monochromatic, and that means that we can focus them really tightly. And if you can focus something tightly, you can put lots and lots of energy on a single little point, even down to the size of an atom. And when you put that much power on an atom, you drive it hard. You drive it as if it was in the Big Bang. And that actually happens at a laboratory, also of the Department of Energy, called Lawrence Livermore, with the National Ignition Facility. So we don't do that kind of laser. What we do is an equally fascinating and equally interesting laser called the free-electron laser. And so those were first invented in 1977 by an American named John Mady, and this was at Stanford University out on the West Coast. And the really nice thing about a free electron laser is I can change the color. So most lasers, like the laser that I could make from this stone in my ring, are one color and I can never change it. Physics, called quantum mechanics, a branch of physics called quantum mechanics, says that you cannot change that color. With a free electron laser, because the electrons are not bound to nuclei, they run freely in a vacuum, I can tune that wavelength. And we have tuned that wavelength. We have made free electron lasers that work from the microwaves, millimeter waves actually, something that the wavelength's long enough I can hold my fingers up, all the way to X-rays, very hard X-rays. And you can make the output from this laser very high because there's no heating. There's no heating in a gas or in a liquid or in a solid. Next, please. So the history of the free electron laser is that in 1989, two scientists, one still at the lab, a gentleman named Jeff Kraft, proposed that we use that superconducting radio frequency technology to build an FEL. And because the superconducting radio frequency technology lets the electrons flow continuously, just keep running, we should be able to make the power higher. That got our first director, Herman Grunder, really excited. He saw real advantages of that. But he needed to find somebody who could be a good apostle. actually a couple of apostles, to explain just how good it was. So he hired 2 scientists. I've had the great fortune to work with both of them. And they built the case for the FEL. And so in 1994, there was a team assembled, and we submitted a PDR, which means a preliminary design report, to the Department of Energy to build an FEL. I was on that team. That's when I first came here. And then in May, we pitched our proposal for $27 million. And what we proposed is that we would use this energy recovery at a very high beam current, and we would do all these wonderful things. So we would micro-machine materials, we would do processing of polymers and things like that. And the Department of Energy said, oh, this is great, but we're broke. So we can't fund you. We're really sorry. But we'll let you use spare parts from CEBAF. So Herman Grunder, our first director, is a very clever, very resourceful man. And so he was up in Congress, and or actually up on the Hill, and he got this word that, okay, we're not going to get any money from DOE, so what are we going to do? So he goes and he knocks on Herb Bateman's door. Does anybody remember Representative Bateman? Yep. And he went over and he knocked on Senator Warner's door. And of course, Senator Warner, this would be not Mark Warner, but our former, and John. And both of them were very enthused, very excited. And they said, okay, we can't give you $27 million, but we can give you 9. So we can build 1/3 of what we wanted to build. And we did that. And it was a rip-roaring success. So much of a success. And the reason we built it was to help the Navy out. The Navy has this problem. And the problem is that they have these very expensive carriers that cost over $1 billion, have some of our very brave people on them, and they can get very badly damaged by a $200,000 cruise missile. So they're looking for a laser beam weapon to protect them. So we were very successful, and so they gave us a little more money, and we built this. This is actually a schematic. We actually built this thing that's 210 feet long, lives like in my little write-up on my bio, it lives down in the vault of the FEL facility. It's underground because we can use the earth to shield us, and earthworms don't vote, so they don't complain when they get just a little tickle of radiation. Upstairs, we've got all these labs. That's the important thing. We make the light down in the vault, we bring the light upstairs with mirrors in a very good vacuum, and then we distribute the light into the different labs. We have all these different labs. Just to say what some of these acronyms mean, of course you know what NASA is. THZ means terahertz, so that's very long wavelength light that passes through your body. Actually, it passes at least a few millimeters through your body. But it doesn't ionize, doesn't cause any cell damage. So terahertz is very useful. PLD stands for pulse laser deposition. LMES, that's the laser microengineering station. And there you have it. So some of our applications really quickly, some of these very exciting applications. So one of them I mentioned earlier, metal surface treatment. So one of the most important technology advances that we've done in the 1900s are turbines. And you might think, well, what do you use turbines for? Well, one of the biggest one is the lights. The electricity that powers our lights are made from turbines. Powers come from turbines. You've got to heat water, you make steam, you push the steam past a turbine, and the blades, they have blades just like the turbine on a jet. But the thing is, when you shove steam onto metal for any length of time, it gets brittle, and you've got to shut those steam turbines down and replace the blades. So anybody who works at Surrey or has a good friend who works at Surrey nuke plant like I do, periodically, about every 6 months, that person kind of vanishes for about 6 weeks because they have a shutdown. They've got to replace all those turbine blades. So imagine what you could do if you could make the blades last 10 times longer. Turns out you can do that. You can take the laser, shine it on the turbine blade, move it really fast, and you can heal the metal. You actually convert the surface of the metal to a glass. And we all know that glass resist steam, resist heat pretty well. So that's one of the things, and we've been working with Dominion to do that. We make these boron and carbon nanotubes. And so there's a picture of a nanotube over on the right. And they're very small. They're less than 1 micron apart in size. And you might say, well, what's a micron? Well, your hair, if it's really, really fine like mine, is about 25 microns. And if you have coarser hair, you're about 50 to 80. So it's smaller than a human hair. And what you do is these things are stronger than spider web. So you can make really light, really strong structures. And people are actually, due to some of our work, making things like bicycles, racing bicycles that cost $15,000, $20,000 with that. Another thing, laser nitriding. And you go, what's that? Well, can you go back one, Michelle? Thanks. Okay, so one of the things that goes on is automobiles. So have you noticed that people aren't quite as insistent, although if you're under warranty, you should get your oil changed every 3,000 miles, but you know that you can go a little longer and it doesn't kill the engine. Well, Audi has found a way to use lasers to polish the inside of the cylinders, and it makes them go over 100,000 miles between oil changes. And the way they do that is they actually insert a laser. There's your cylinder block. Oops. There's the cylinders. And they actually insert this laser down into it, and then them being Germans, they spin the whole engine block. If they were Americans, they'd spin the laser beam, but whatever. So what happens is they run 5 simultaneous lasers to take care of all of this. And there's what happens. That's what the surface looks like before the laser treats it, and then look how much smoother. And then look what happens. You reduce your oil consumption by 30 times. You can go a lot longer, and the engine performs better. Well, it turns out that they went out, the scientists that proved this process went out and used the free-electron laser, and it works even better. So there you go. Another purpose for the FEL. Now, would you go build an FEL to go and hone cylinder blocks? You could. But what's better is to use the FEL to build a laser that you could then take to your company, and it mimics the FEL. See, it costs millions and millions and millions of dollars to build one laser to test something. And what if you tested wrong? What if it didn't work? Where you can come out to the FEL, you can use it for a day, for $10,000, and you're way ahead. Another one, differential heating of fatty tissues. So this is the publicity. And this was really, we got a lot of publicity on this one. So what we do is the free electron laser can tune. Remember, I talked to you about how you can change the color? And what you can do is you can tune it to a particular color where normal skin, which is mostly water, the laser goes right through. And fatty skin, it absorbs the fat, it gets hot, and the fat cells die. And then the body just cleans it out. So, of course, my colleague, Rox Anderson at Massachusetts General talks about acne, and didn't really talk about cellulite, but we were all going, laser lipo, yes. And so I offered, in the name of science, to wear like, a foil, glasses and stand up and pirouette in front of the FEL, and it didn't pass safety, so darn. If you go on to the next one, why don't you just pass that one? Okay, so I don't want to go into pictures of the laser absorption spectra. I don't think you're going to care about that. But it was very, very important because adult acne, in all seriousness, adult acne is a big problem. And the primary chemical, the primary drug that we used to use, the one that I took, and they said, don't get pregnant, as if I wanted to get pregnant for other reasons, at 17, was to cure acne. But the problem is that some gals do get pregnant on Accutane, and it will deform their baby so much that they have to have an abortion. So Accutane's a real problem, and we need to find a new way that doesn't involve drugs. So now we have a laser system that when you get older, if you need to be treated for acne, you can just shine this laser light on you, and that takes care of it. The other idea is killing plaque, or basically dissolving plaque and cholesterol in your arteries. What they want to do is, rather than use the system that we have now, which can actually break off pieces of plaque that then travel through and maybe cause a stroke in your brain, instead what you'd like to do is take a little catheter, shine that color of light on this fatty tissue, the plaques, and then they'll just dissolve. So they basically melt it, and then your body, your kidneys get rid of it. So it's just a fantastic stuff. Thank you. So then the last bits are, we can use this. We have a UV FEL, and here are all the different things that we can do. Since I don't have a lot of time, I'm going to go ahead and ask for the next slide. What do we use our FEL, the ultraviolet, for? We build microsatellites. Actually, we make nanosatellites that are no bigger than a salad plate. And here's a picture of the parts. So it's COSA, which is the Co-Orbiting Satellite Assistant. This is a little satellite that would sit in the palm of my hand. It's as big as a dinner plate. And in space, it can fly, turn over, spin around. And the whole idea is that you can fly around the space station, around a shuttle-like spacecraft, and check it out. It takes 170 hours to build one of these with a conventional laser, and with our FEL, it takes 15 minutes. Next. To make all that work, we've got this fancy table with all these optical parts, so I just wanted to show you a picture. So finally, I want to talk about dark matter. So I've talked to you about the matter that we sort of understand, right? That's the baryons. Remember, baryons composed of fermions. And then the hadrons, or baryons, are fermions and bosons. Well, it turns out that all of that is only 5% of the matter in the universe. What we know from a lot of experiments that have been done since the 1920s is that there's far, far more matter, as evidenced by gravity, than we can detect. So of the 5% that we are, there's actually a total of 27 or so, it should be 22.2, sorry, bad math. So there's 22, so the total matter density, all the matter divided by the volume, is 27.2%. So the question is, what's this 22%? And we call it dark matter because we only can detect its presence from gravity. It's dark. So we actually we were pretty sure, and when I say we, I mean all the physicists and scientists and astronomers in the world, think it's due to some subatomic particle. So at Jefferson Lab, we've been working to try to figure out what that particle is. Next. I'm actually going to skip past this with one statement. We're either look at WISPs or WIMPs. So if you want to go look up WIMPs, put in all capitals, WIMPS, or look up WISPs, WISP. We did a WISP search with the FEL, and we were, for a long time, we were the leading experiment to try to look for what are called WISPs as a candidate for dark matter. And Michelle, if you hit the next, we used the CEBAF to do a WIMPS experiment. So these massive detectors that are taller than a person, way taller than a person, we shot the electron beam into it. And this is the team of scientists that did all that experiment. And that was run in the summer of 2010. In neither experiment did we see anything. So kind of in conclusions, what you've got in your own backyard is a world-class, unique laboratory facility that we use to explore matter. We have 2 unique accelerators that operate completely independently to answer some of these very fundamental questions. We're upgrading the CEBAF machine right now. Actually, we're upgrading the FEL too. And with all these improvements, we continue to make, I think, a very major contribution to society and also to our community. And so finally, I'm not going to read it, but if you'll hit the button there for me, thank you. I have a quote by Thomas Jefferson. And so on that note, thank you very much for your attention.
We have
Are there any questions? Yes, sir.
You talked about the economic impact of the laboratory, but I didn't get the human capital, the scientific prestige and status impact. Could you say something about that?
Yes, so I think everyone heard the gentleman. Michelle, can you go back to that first slide? But I guess the question that what you're interested in is you saw how much in dollars, and you saw a jobs number. So we sort of, in the United States, we sort of offer up about 2,000 jobs to the nation. If the J-Lab went away, there's 2,000 jobs, most of them in Hampton Roads, that would go away, and around, at this point, $250 million. But in terms of experiments, we generate of order, I think it's about 500 scientific papers. Actually, it's probably more than that. It's at least 500 papers every year. We also generate, speaking for myself, I've generated co-generated 7 patents. We also generate of order 50 patents per year. So those are given to the United States government free of charge because, of course, you paid for them. The United States government paid for that. So if the U.S. government, say the U.S. military needed it, they get it free. But on the other hand, if some country, some scientist, or some industry in some other country wants that, then they pay that money to Jefferson Lab, which then goes back to the United States government. So there's a lot of prestige. We go all over the world. I just came back from a conference in Japan, so we give speeches all over the world. The FEL, not just the FEL, but the CEBAF, from nuclear physics, that is the premier facility in all the world. There's no other facility like it. And so there's an enormous prestige associated with that, and I hope that kind of answers your question.
Thank you.
You're very welcome. Next, any others? Yes, ma'am.
What about the other automakers? Will Audi let other automakers copy what they've done?
Absolutely. Yes, so the question was, so I showed you the example of Audi and what they're doing with their excimer lasers. Excimer lasers are a particular laser that was used for a long time to do eye surgery. And I think, in fact, it still is used a lot. And so Audi was adapting a commercial product. They published this information. You know, the picture that I've shown has been shown at lots of other scientific conferences. So everybody else knows about it. And I know that in particular, I've talked to people at Ford. Ford is also looking into using laser honing to treat their cylinders. So yes, there's every plan. And with the research that we've published using the free-electron laser and its unique characteristics, they're working on building a laser that replicates the FEL, but that can sit on a machine shop floor and work in that kind of nasty environment compared to the FEL, which sort of likes pristine environment. Yes, ma'am.
Very early on, you spoke about like trying to separate the quarks from each other, and then
you make new quarks.
Yeah. Are you really making new, or is this something, you know, like is dark matter seeking its way in there, and we can't make something out of nothing?
In fact, there's something made out of nothing happening all the time. And it's kind of, there's a whole talk I could give you about that. So let me stop back and let's just, so the question was, remember I mentioned that when we put more and more energy trying to split the atom, trying to split, not just split the atom, but split the protons or split the neutrons into their quarks. If you try to pull the quarks apart, you actually form new quarks. And I made it sound like it was out of nothing, but it's not, because remember, what was I doing to pull the quarks apart? I was using energy. And remember, E equals mc squared. So once you put enough energy in that E is equal to the mass of the quark and the anti-quark, then not just is it possible, but it's almost fundamentally has to happen that you will now produce out of, you'll borrow the energy and convert it to mass. And that forms a meson. Now mesons have this interesting property. They don't live very long. They live a few thousandths of a second. So what happens when that quark and anti-quark decay? The meson decays, and what happens? the energy comes back out, and it comes back out as X-rays. So we never cheated. We never cheated. We played a shell game, right? We played a little shell game between energy and matter, but we didn't cheat. But in actuality, something called virtual particles. So virtual means, as you might guess, they don't really seem to exist. Virtual particles actually pop into existence, live for a few billionths of a second, and then disappear. And because they came out of the nothingness, so to speak, with what's called vacuum energy, they borrow a little vacuum energy, appear for an instant, and then put the vacuum energy back. And we can actually prove that. There was a gentleman named Casimir, Dutch gentleman back in the 1930s, that made a proposal. He said, what happens if I take two plates, two long plates, I put them in a vacuum, okay? I put them in a vacuum, and I put them very, very close together. What happens? Well, they don't quite snap. My friend here, Sheldon, said they snap together. They don't actually. They slowly drift together. They don't drift together because of their gravitation. They drift together because there are more virtual particles in the universe than there are with different wavelengths than there are in this little tiny gap. You can only form so many virtual particles in this little tiny volume, and then you've got the rest of the universe. So the rest of the universe is pushing on those two particles from the force. It's amazing stuff, isn't it? That right there, right in front of you, virtual particles are created and then vanish in a blink of an eye.
I think we're about out of time.
Are we about out of time? Well, listen, thank you very, very much. I'm going to be here for a few more minutes. If anybody has any questions, come up and talk to me. You want to, well, go ahead.
Baryon, could you define that again, please?
Sure, a baryon is like a proton or a neutron. It's got a charge, typically a positive charge, and it's made up of 3 quarks. All right, thank you very much.
And thank you, Dr. Shin. I took physics in high school, but I think you lost me about after the first 10 minutes. But yeah, it was very, very interesting, and we appreciate you letting us know what's going on just right across the river from us.
You're very welcome.
I want to remind everybody that in February on the 12th, we will have Dr. Laurinette Lee along with her comrade, Paige Newman, and they are going to talk about this database that they have created in the Virginia Historical Society of slaves. They have done a huge amount of research and have traced the genealogy of slaves in the state of Virginia. And it is online on their website, but she is going to talk about all of the labor and research that it took to create this database and make it available to everybody. And I hope that most of you all will come back and visit us in February. Thank you again.